interferometer on the previous class. Now, the topic that we will cover today is Stokes treatment. So, as we considered before, we consider a light of amplitude small a incident from air to the surface of water. Part of it will be reflected and a part will be transmitted. The reflected part will have an amplitude A into a small r, where a small r is called the reflectance. The transmitted wave will have a amplitude A into small t, where small t is called transmittance. The reflectance is the ratio of the light reflected to the light incident, and similarly transmittance is the ratio of the light transmitted to the light incident. So A is the amplitude, R is the fraction of amplitude reflected, and this is from rarer to rarer medium. It will be different for different medium. The value of both R and T will be different for different medium. It will be fraction of amplitude transmitted from rarer to denser. Now what Stokes said, that if there is no dissipation, dissipation means that the energy is lost. If there is no dissipation of energy by absorption, a wave motion will be a reversible process. That means if there is no loss in the energy by absorption, then we can backtrace the phenomena. Let's see. Here you see that an amplitude A is coming, AT has been transmitted, AR has been reflected. Now these reflected and transmitted are coming back. AT which was transmitted in this direction is coming back. AR which was reflected in this direction now is coming back. So after reflection, its amplitude will be, it will be multiplied by R, and this light, this will be reflected and part will be transmitted. The transmitted will have an amplitude multiplied by small t. Now consider this light. This light will be partly reflected but this is being reflected from a denser to a denser medium, so there will be a different reflectance. We call that reflectance as r dash, and a part of this wave will be transmitted, and the transmittance is from the denser to the rarer medium, and this transmittance will call as t dash. So r dash is the fraction from denser to denser, and t dash is the denser to rare. Now, what Stokes said, that if there no energy is lost, then we can backtrace this wave. So for this to happen, these two waves should, in total or after superposition, give me this wave. Only then what Stokes said will be valid. So, and now consider this line. There was no such ray here. So these two amplitudes will add to give 0. This is equation 1A, this is equation 1B. I will take this term on the right hand side. Similarly, from equation 1B, I will take this on the right hand side. These two are called Stokes relations. Since we know that intensity is proportional to amplitude square, so from conservation of energy, r square plus t square is equal to 1. And in this case, t cannot be equal to t dash. Now from equation 2a, we can see, just see this. This is equation 2a. You can notice that if intensity is proportional to the square of the amplitude, then that condition is valid only in one medium. If there are two mediums, then this kind of term will come and the intensity will not be proportional to the square of the amplitude. Rather, it will be a multiplication of two different amplitudes. So how these two are different? There must be some property of the medium that will affect the transmittance or the reflectance. So and that property is called refractive index. Now the value of refractive index will determine the intensity of the light in a medium. Now the second thing that we can see from this relation is that energy of the beam is important and not the intensity. Because intensity will depend on the refractive index which is changing. So for law of conservation of energy to hold, we should consider the total energy of the beam instead of considering the intensity. From equation 2b, we can say that the reflectance is same on either side. This is the second relation. R is equal to R dash. And now we see this minus sign. The negative sign denotes a phase change of pi. And that is why we say that when a light is reflected from a denser medium, there is a phase change of pi. So these are the Stokes relations. Now we will revise our concept of thin film. What happened in thin films? A ray was incident. So the light will come it will be transmitted into one part will be reflected. Another light will come from this one. It will be incident here. Part will be reflected and part will be transmitted similarly. And all the transmitted beams will interfere with the help of a lens and give me a pattern at point P. So consider another diagram. This diagram we have already seen previously. Light is incident at an angle phi. The angle of reflection will also be phi, and the angle of transmission. So the angle of reflection is phi dash. This is phi dash. Now it will be incident on the second surface, reflected from this one, and will be transmitted. So we are considering interference between these two transmitted beams. This light will travel the path AD, while this light will travel, this way will travel path AF plus FB in a medium of refractive index N, and the small d is the thickness of this plate. So the path difference between 1 and 2 now consider these two triangles. These are equal angles. This is common. This is 90 degrees. This is 90 degrees. So they are congruent triangles. Therefore, AE is equal to EG. AE is equal to EG. And AF is equal to F. Now, since this AF is equal to FG, so we can write AF as FG. Now, FG plus FB will be equal to GB. This GB can also be written as GC plus CB. Now consider the triangle ADB where sine phi, this triangle, this is phi. Sine phi will be AD upon AB. So AD is equal to AB sine phi. We will substitute this AD here. No, we will not substitute it right now, but at a later stage. Now let us consider this triangle AC. Here sin phi dash will be equal to CB upon AB. We will divide these two from Snell's law. This will be equal to the refractive index. Now AB is equal to N into C. We will substitute this value. This is also N into CB and this is NCB. So we will be left with N into GC. Now let us consider this triangle ACG. ACG. Here the cos of phi dash will be equal to GC upon AG. Cos of this angle will be so GC AG cos. And AG is this, and this is AG can be written as AE plus EG, and both of them are equal, so I can write it as twice of AE. And A is equal to small d. So this can be written as now when this path difference is equal to whole number of waves, multiple of wavelength, then this will give me minima. And when this will be not multiple, then this will give me maxima. This we have already studied. Now we will define fringes of equal inclination. If phi is 0 degree, then phi is 0, that means phi is 0, that means the light, this is 0, that means light will come along the normal. The light will be incident along the normal. So for minima, phi is equal to 0, we will get a dark fringe. Here we can see that if the thickness of the plate is large, then the order will also be large. If the thickness is large, then M is also, the order is also large. A large value of M will signify greater number of orders. That means that the distant source is bright, which can only be possible this will give me a clear image. The more the number of orders, the more clear is the image. For a specific value of 5, and since d is also constant for a plate, so for a specific value of 5, we will get a specific order. So all the interfering orders will be equally inclined, and such fringes are called Haidinger fringes. And when these parallel beams are brought to interfere with phase difference determined by the angle phi, angle of inclination, then such fringes are called fringes of equal inclination. So today we will start with the topic. We will be our next topic is fringes of equal thickness. So we start with this topic. Now we are going to study fringes of equal thickness. Like we talked about while discussing about fringes in Michelson interferometer, we talked about fringes of equal thickness when we have two plates which are inclined at any angle and light from the source is incident. And here is the observer. So these are the glass plates so when we see this kind of a situation, when the glass plates are inclined and there is a wedge shaped film formed, the film is having a decreasing thickness. The air film formed between these two mirror glass plates is of decreasing thickness. Thickness here is more and it is gradually decreasing. So in Michelson interferometer, what we said that if the two mirrors are in an inclined position, we were getting straight line fringes. So similar will be the case here with this wedge shaped air film. Such a kind of film with decreasing thickness is called wedge shaped film. So the fringes in this case are straight, and all the fringe lines have the same thickness. And the condition for maxima is, so if this condition of maxima is satisfied in a wedge shaped ear film, we will get fringes of equal thickness